Well, hello retro computing enthusiasts. Welcome back to my channel. Mike here. And it's time for episode 3 of working on my JAZ80 breadboard retro computer here with the Z80 processor. Left off in episode 2, had gotten the larger EEPROM working in here. So now we've got a 27C256 EEPROM in here with 32K of program space in it. Got that all working. We're running my little LED scanner program out of the EEPROM. Everything's working great. Now I know it has been a little while since episode 2 came out. I had planned on doing a whole series of these episodes in fairly rapid succession on the JAZ80, but I got a little bit distracted by my Nabu computer when it arrived just before Christmas. And pretty much for the last couple of months I've been working on the Nabu almost exclusively. There have been a whole series of videos. I think I'm up to 12 now on the Nabu. Basically when I got that computer I just ripped the EEPROM out of it and I wrote all my own firmware for it. Basically bootstrapped myself up from the bare metal to a working system. So if you're interested in seeing those videos, I'll put a link in the upper right and you can check out the Nabu playlist. And a lot of the software I was intending on using in the JAZ80 wound up on the Nabu. So it got a little bit of a test run, but I had to modify it a little bit to work with a different architecture over there on the Nabu. But at least it validated that what my plans I have for the future of the JAZ80 I think are very doable. So in this episode, what I want to do is I need to rework the I/O addressing, which is down underneath this mass of wires going to the RAM memory. I am not Ben Eater when it comes to wiring breadboards, okay? I apologize up front if this mess offends you, but hey, it's working, okay? So I don't get a lot of extra points for style, but for function, I'm right there. So I want to redo the I/O addressing, which is down here. I'm going to take out the dip switch and the 74244 input port here because they are no longer going to be needed. Alright? I'm going to replace this 74LS373 with a 74LS374 because this 373 won't work with the new I/O addressing scheme I'm going to be implementing. I would like to add a new clock oscillator up here for the eventual serial port, 1.8432 megahertz clock oscillator. Get that installed, and if we get all that done in a reasonable period of time, I want to install the Z80 CTC chip and then see if we can write a little bit of code that's going to test both the new I/O addressing scheme and the CTC chip and see if we can get it outputting a clock rate that we need for our serial port, which we're going to put in eventually. So that's a lot to do in one episode. We'll see how far I get. May have to cut it off short if this gets too long, but let's get down to it. So before we get started, let me address a couple of things. First off, all of the firmware I'm going to write in this episode and future episodes will be on my blog, and I'll put the address of the blog on the screen right now so you can check that out. There's also all the other information in this series that you need is there. There's schematics, bill of materials, references for everything I use. There will be links to all the videos in the series. It'll all be there. I don't have a GitHub account. Thinking about it, but I never seem to get around to it. But you know what? I've been releasing stuff on my blog since long before there was GitHub, so I'm just kind of used to doing it that way. It seems to work. So go check out my blog. Another issue, I got a lot of questions after the first couple of episodes came out about what sort of breadboarding system am I using here. So let me zoom out and show you exactly what I have here. Now I don't know if this is still manufactured or not. This is fairly old. I actually got this from my brother, who was also, before he passed away, he was kind of an electronics nut too, and he did a lot of work on this for a lot of years. And the breadboards that are actually built into it were kind of beat up, and not very reliable anymore. So I have put a whole new set of newer breadboards over the top of the old ones. So you can see it's kind of thick there. There's 2 layers. But it has plus 5 volt power supply and plus and minus adjustable power supplies up to 15 volts or minus 15 volts. Like I say, I don't know if this particular one is sold anymore, but I will put a link in the video description to one very similar to this that is available now. And all of the other stuff I use in this series, there will be links to it in the video description, okay? So here's a quick look at my workspace. Several people have asked about my workspace and how I put my camera up and all that. I've got sort of a redneck camera boom I've built over here out of a piece of 80/20 strut on my tripod, and it needs a counterweight, but I'm using bungee cords instead. And camera's over here pointed down at the table. The room is kind of cluttered because it's small and there's a lot of stuff in it, but I try to keep the work area fairly neat. I've got a ring light with a magnifier in it and another light aimed down. 3D printer in the background right now is just acting as a support for my laptop computer, which has my EEPROM programmer on it. And let's see, here's the JAZ80 computer, my little IC repository for the chips that are going to go into it, hookup wires, pliers, and schematics. And that's, and then there's a laboratory notebook back there too. So that's my workspace right now. So for those of you who were interested. So anyway, let's get back to work and get down to business here. All right, I talked about wanting to redo the IO address decoding, and I'll show you why. I went over this in the last video, but here's what we got for IO address decoding now. It's pretty rudimentary. Basically, any IO read or any IO write goes to the onboard input and output registers here. And well, that needs to change. Going to have a lot more complex IO scheme because I'm going to have a lot more IO ports on here. So we're going to go from this to this. We're going to replace that quad OR gate in there with a 74LS138 3-to-8 decoder. And that's going to give us a lot more flexibility in our IO decoding. So I think that's where we're going to start today. So I need to carefully move all of these memory address wires out of the way so I can actually get to the chip down there that I need to replace and all of its associated wiring, and start modifying things. Fortunately, the output register over here, well, I need to change it too. Okay, gotta do this in a certain order apparently. I need to change out this chip as well, so before I move all the wires over the top of it, I think I will change out that chip. And then we'll go over here and take out this chip and modify the wiring for the new addressing scheme. Okay, I think that is probably the better way to go. I don't have to move these wires too many times, because certainly something will come disconnected and it will take me an outrageously long period of time probably to figure out what went wrong. So this is a 74LS373. It is this output register right here, but we need to change it to a 74LS374. Fortunately, they have pretty much the same pinouts, so I should just be able to pop that chip out and pop in the 374. What's different about them is the enable on them for latching the output is different, and this one won't work with the new IO decoding scheme, but this one will. So that's why I need to change that one out. Okay, let me get the new chip out of my little IC chip repository here. So I've got a couple of 374s here. Yeah, there it is. Here's the 374. Well, I might as well leave this open because I can pop the 373 in it once it comes out. Now, over on my main channel, Omega Geek 64, I break down e-waste to recover the gold and silver they contain and other precious metals. But not everything gets, you know, rendered down immediately for its precious metals. I will salvage useful bits for my electronics projects. And all of the chips I am using in this project were salvaged from e-waste. Just yesterday, off camera, I tested this chip to make sure it's good since it was salvaged from e-waste. And my EEPROM programmer has the ability to test logic chips as well. So I've tested it, it's good, so we're going to put it in. If I can get it in through this nest of wires. Getting the old one out was no small feat. Yeah, it doesn't want to go. I don't want to bend any of the pins getting it in. Let's see here. Move this wire out of the way. Maybe that'll help. Now I won't be able to test if this change works until I get the entire new IO address decoding scheme up and running. Uh-oh. Yep. I knew that was going to happen. I'm pulling out memory wires. Okay, so I've got at least 2 of them loose over there. I'm going to have to figure out where they go. Okay, so this is kind of a tedious process. I won't make you watch all of it. Let me get this in and try not to pull out any more memory wires, address wires here, and I'll be back when it's in. Okay, that was a bit of a hard-fought battle, but I got the 373 out and put in the 374. I have reconnected the lines going to memory up here, the RAM memory, and I've pretty much exposed the 74LS03 down here, or 02, that I need to take out. And let's see, there's a lot of wires down here that are no longer going to be needed. This one here is going over here to the input latch. Well, we're not going to be having an input latch over there anymore, so this wire can come out. And then I can pull the chip out. I'll put that back in my repository. Now I'm going to need to get rid of a lot of this other wiring that makes no sense anymore. Over here. It was around this 03. And then put in the 138. Now there is one wire we're going to need, and I'm pretty sure it's this yellow one, which should be IO request. I will set this just out of the way over here, and then pull out the rest of this unneeded wiring. Hopefully my head's not getting in the way. Can't see the viewfinder on the camera while I'm working. So this one I think is right. or read. Either way, I don't need those anymore. So that one would probably be write or read, and this one here would be this one here, I think, is the enable for the output port, which we do want to keep. This one must be write or read over here, the green one. I really should have put a little more thought into the color coding before I did this. Like I said, I'm not Ben Eater, but I'll get there in the end. Now, I don't have need for these lines coming from the processor anymore for I/O decoding, but they will come in handy in the future for other things. So I'm going to pull them out here. Rather than pulling them out entirely, I'm just going to get them out of the way. Sort of fish them through all this other stuff. Get them over here out of the way. Let's see, that's my reset line right there. We need that. And this one is, yeah, this is the enable. Yeah, this one's the enable for the output port, which we're going to need. Okay. So, I guess we're ready to put in the 138. So let's see here. Nope, that's not it. That's the O2 I just took out. There we go. I actually didn't have a 74LS138, so this is a 74HC138. It should work just fine, and actually would be good for possible future speed increase. Certainly, it's going to put less of a drain on the control bus lines than an LS chip would, improving fan out. Although I don't think we're going to have fan out problems with this. So this is a 16-pin chip, and what came out was a 14-pin chip. So I need to move where the plus 5 volts goes into the board here. And let me see if I can get this in now. And there it is. Okay, it's in. I'll move this capacitor over here. Okay. So that's in. So let's see, I decided this was the enable line for the output port. So that's the output port right there, UPWR I've named it. So that needs to go to pin 9 on the 138. So let me see if I can route that to pin 9. 8, 9. There we go. Alright. This is IO request. So IO request needs to go in at pin 5. That's going to be easy peasy to get to pin 5. One, 2, 3, 4, 5. All right. So, what else do I need? I need a 2, 3, and 4, and a 7, and I need the M1 signal going in there. Now, some of you might be wondering, why do I need M1? Well, it has to do with interrupt acknowledgement cycles. And during an interrupt acknowledge cycle, M1 and IO request are both low, okay? And I do not want to decode the IO during an interrupt acknowledge cycle. So I need to have M1 in here to disable IO decoding. Now, at the moment, I'm not using interrupts on this board, but I want to keep that as an option for the future. And in fact, as we put in the Z80 family chips here, I want to hook up their daisy-chained interrupt wiring on them. So even though initially I'm not going to have any interrupt handling code, I don't want to lock myself out of using it in the future. So our I/O decoder will not become active during an interrupt acknowledge cycle. So I need to find M1, and I need to find A2, 3, 4, and A7 and route them down here to the board. Now I've got all the address lines right up here at this RAM chip, so that's a fairly short routing. M1, I am not sure. I might have to go all the way back to the processor to get M1 because I don't think I'm using it anywhere else on the board. So I will do that. And I won't make you watch the whole tedious process of wiring it up. Let me just get it wired up, and I'll be back when I'm done. Okay, that was actually fairly easy, not such a big battle. I stole address lines 2, 3, and 4, and 7 from the RAM chip up here and ran them down here to the 138. There was already an M1 line that went over here to an LED that I deleted back in the level 0 machine, which was run by a 555 timer. The cycles were slow enough that you could see the M1 line blinking, and it would actually tell you something about how the machine was working. But now that we're on a full 4 megahertz clock, it just looked like it was on all the time. So I deleted that LED, but I still had the wire for the M1 line going over to where it was, so I just moved that over here. Had the IO request line already going up here. So everything is in place. I routed the enable line, or the latch line, from the output port over to pin 9 where it's supposed to be. And cleverly, when I wrote the test program, the LED scanner program, cleverly I wrote it for the new IO addressing scheme. So it's at 18 hex, which is where that's going to go low, is when we have an address of 18 hex on the inputs, M1 is high, and IO request is low. That should go low, and it should latch this, and any data on the data bus will be latched and displayed on the LEDs. So it worked before because any output port write would go to this latch, but now only, well, actually this is going to cover 4 different addresses, we're only using one of them. But this will cover 4 different addresses. The reason I have this decoded like this is because we're going to put in some other peripherals. We're going to put in a counter timer, we're going to put in a serial I/O, we're going to put in a parallel I/O, and they all use 4 different I/O ports for their command and data registers. So this is all decoding 4 ports here. And so we're going to get 4 ports decoded down here for the user port 2, but it doesn't really matter. We're just not going to use the other 3 for anything. So now it's all wired up, and since the software was already pre-written to use the new IO addressing scheme, if I turn this on, hopefully it's going to work. Let's see. Will you look at that? Wow, look at it scanning back and forth. And I talked a little bit about this software in the last episode. It's not just a pretty LED scanning program. It tests a lot of functions of the computer. It tests that the RAM is working. It tests that that the I/O is working, and basically the processor's running. So it basically tests most of the computer functionality here. Because we've got a delay program that's using the RAM. We've got a stack set up. We're calling and returning from functions. So if the RAM wasn't working, that wouldn't be working. So yeah. So this program, just by the fact that it's running, tells me I've got my new I/O address decoding scheme working. I haven't broken anything. I've got all the wires back in place for the RAM. Nothing's broken. It's all working. Okay, so we can go on to the next project here. Let me turn it off. So what else I want to do here is I want to take out this input port because it's not really doing us any good. I'm not going to be using it for anything in the future. So we'll take it out. Take out the dip switches, take out this 74LS244 over here, and all of its associated wiring. Take out the, get it out. Take out the resistor network over here. That'll come in handy later though. Got all these little jumpers that need to come out in here. Now, I am not just going to indiscriminately pull out wires here because I'm thinking this would be a good spot to put the CTC chip because I've got data lines running over here and the CTC chip needs data lines. So they'll need to be rearranged, of course. But yeah, this would be a good place to put it because I've already got the 8 data lines coming over here. All right, so I will leave the 8 data lines in place for now, roughly in place. These lines here can come out. This can come out. Fish these out of here. And I've got to figure out which of these lines is which data line, because I don't want to mix them up or the CTC won't work. Get this last wire out of here. All right. So there we go. Let me pull this capacitor out, this jumper here out. Okay. Out with the old and in with the new. Yes, indeed. I'm just going to pull these lines out and move them aside for now. Guess I've got to figure out which of them is what. And we will install our CTC chip, which I will get from my repository over here. I've got a Z80 CTC chip here. And we will just stick it right in here. Perfect. All right. And now, is there room? I was originally going to put the second clock oscillator up here, but let's see if there's room to put it in right here next to the CTC. That would be ideal. Looks like there might be room for it. Yes. Straighten the pins out. Maybe. Maybe not. Maybe not quite gonna fit. Okay, so we will put it in up here where I was originally planning on putting it, over here. Those pins are a little wonky. Let me straighten them a little more. They just don't want to go in. Okay, so we'll put that up there. Kind of wasted space, but oh well. And I'll have to run a line all the way down here to the CTC. I suppose I could... it might be better, actually, if I put the new counter chip, or the new clock chip up here, actually, and I'll have a shorter run to the CTC, and maybe a little bit less RFI interference, possibly. So that's a good idea. That's a good compromise. We'll put that up there. I'm sure I'll need another decoder chip at some point, So we've got space for one over here. Decoder chip or glued logic at some point, so we got some space over here for that. And yeah, I think that's going to work. Okay, so I forgot to turn the camera back on. I've put in a bypass capacitor and power for the oscillator. Put in ground. Well, okay. I'm going to have to use a longer wire than that because those LEDs over there are sort of hogging all the ground lines in that area. So let me find a longer wire and come over here and pick up ground. Okay. So I need to go from here to the CTC. So let's see, the output's going to be up here at pin, what would be pin 8 on this. It only has 4 pins, but it's got a 7 pin package. That would be pin 8. So that needs to go to, let's see here, on the CTC. So that needs to go to pins 21, 22, and 23. So 21, 22, and 23. It's a 24 pin package. So 21, 22, 23 right there. I could put some of these little jumpers back in. Okay, and let's find a piece of wire that's going to reach. Some out earlier. Ought to be long enough. Okay, so I still got to add power and ground to the CTC chip, and you really need to check your pinouts on these chips because they don't all follow the convention of having, you know, ground here and power here. Now on the CTC chip we do have plus 5 volts at pin 24. Which is normal, but that is not the ground line down there. That is, what is it, pin 12, that's the interrupt. So pin 5 is actually the ground line on this chip. So that's the one we need to ground. So you gotta be careful. They will throw you for a loop every once in a while on this stuff. 1, 2, 3, 4, 5. Okay. You'll get sort of into automatic mode wiring stuff up and find out, oops, you screwed up. Okay, but pin 24 is plus 5 volts, so we will connect that up to the plus 5 volt rail. And I'll put a bypass capacitor in there too. Which I need to get some more bypass capacitors. I don't have any more on the table, so let me go find those. Okay, some capacitors here. There's going to be a few more ICs going into this board, so I'll throw a few of them into my IC chip repository over there so I can pull them out as I pull out the ICs. Okay, there we go, another bypass capacitor. So I need to sort out these data lines. Now the data lines are going back to this 374 was a 373 chip. So I should be able to figure out which data line is which by looking at the schematic here and running the appropriate ones over to the data lines on the CTC. So let's see if I can figure this out. So D0 is at pin 3 over here. It looks like which one of these? This is going to take a little figuring out. Okay. I won't make you watch me try and figure this out and look at the top of my head as I'm in here working on it. So I'll be back once I get it figured out. Okay, some of you may have noticed the mistake I made earlier and were screaming at your computers or phones. Yeah. After telling you to double check the data sheet for where the location of the power and ground lines were, I put the power line in wrong. It does not go in over here. This is a 28 pin chip, not a pin 24 pin chip. So even though the data sheet says pin 24, that's not pin 24. Pin 24 is down here. Okay, because I figured this out the hard way, because pin 24 is actual, or pin 28 is actually D3. So this needs to go over here where that was. All right. And the power needs to come in over here. Let me move this decoupling capacitor over a little bit closer. Not that it probably matters much, but should be as close as possible to the power lines. Okay. Yeah, that's a little... wiring's a little goofy, but okay. So that should be right for D0, 1, 2, and 3 now. And then these others would be for D4, 5, 6, and 7. So I just need to get them plugged in where they belong, which according to my sheet are 1, 2, 3, and 4. So okay, so let me route these correctly. And then we're back. Okay, so I've got the 8 data lines for the CTC hooked up. I've got the chip select, M1, IO request, and read all run over there. I still need to get A0, A1, reset, and the system clock line over there. And then we should be done wiring it up, and we can do some testing. So gonna have to do a little bit more wiring. So I can get again A1 and A0 I can get from the RAM chip up here. It's not too long a run. Let's see, system clock and reset. Well, if I have to, I can run all the way down here for the system clock, and well, reset I can get from right here at the reset button. So okay, let me get those 4 lines run, and then we should have the absolute minimum we need hooked up to the CTC to actually see if we can initialize it and get the bit rates out that we want. Alright, so now I've got the CTC hooked up with the bare minimum of what we need to program it up and see if we can get the bit rate we want out of it for our eventual serial port, which isn't here yet. But this is a good stopping point if I can get this working. Alright, let's make sure we're getting the right bit rate out of this that we want. Well, we actually seem to be getting nothing out of this clock oscillator. Ah! I see the mistake. I'll bet some of you saw it too. I've got the power going in the wrong place. Let me see if I can fix that real quick. The importance of testing as you go. You know, not just assuming that you got everything right. And I think I messed up again. That is not the right place. That is the right place right there. Let me move this capacitor over here. And then we'll check it again and see if we're getting what we want. It's a little dark down here. I'm having trouble seeing because I was getting a bad reflection on the camera off of the oscilloscope screen. So I turned my ring light off. Now it's a little dark for me to see what the heck I'm doing. Okay. Let's see if we're getting a signal now. There we go. Yes, 1.843 megahertz. I don't know if that's showing up on the camera, but yes, 1.4. 1.843 megahertz square wave going in there. There, that's a little bit more visible. Alright, and it's coming down here to the CTC. Yes, so the CTC is getting its external clock input. Alright, excellent. Okay, so now it's time to write a little bit of code, I think, and see if we can get the bitrate frequencies that we want out of the CTC. We have to initialize it for that, so let's go write some initialization code. Okay, it's the next day, and the first thing I did this morning was go back through here and re-verify every single connection to the CTC. I guess I was not fully awake yesterday because I wired some stuff up wrong. So I came back through here and just made sure everything is connected up exactly the way it's supposed to. I started noticing the errors that I was doing yesterday, so everything's fixed now. Every single connection to this 28-pin chip, 28, I thought it was 24 at first, it's 28, it has been verified that it's going where it's supposed to go. I was having one problem with the reset line, which is this red wire here. It's very taut and it keeps pulling out, and while I was pushing it back in, I noticed that my reset circuit wasn't right. I still had the larger capacitor in there that I had when I was running this thing off of the 555 timer circuit instead of off the crystal oscillator. So I have fixed that. So the reset circuit now conforms to the schematic. But it did remind me that I have not liked this idea of a reset circuit from the beginning, and I think an unscheduled change, maybe in the next video, we will revamp the reset circuitry and make that a little better. Maybe I can use either this unused space over here or this unused space over here for a better reset circuit. We'll see. Anyway, let's go write some code and see if we can program up the CTC and get it to output the bit rates that we want for the SIO eventually, which is going to be coming along in a future video. So let's go write some code and see if we can make that work. Alright, so here we are in the ASM80.com online assembler. I like this online assembler. It's very accessible for anybody who wants to follow along with this project at home. You don't have to try and find an assembler that's going to work on your computer. And you know, it's online, it's easy. So here's some firmware I've written to initialize the CTC. As you can see, it's a very short and simple program. In fact, not all of it has to do with the CTC. We've got the diagnostic port in here because we're going to output some data to the diagnostic port to let us know that the program is running right. And then we have some equates up here for the different channels of the CTC. These are the addresses of the 4 channels of the CTC. Channel 0 is at IO port 8. Channel 1 is at IO port 9. Channel 2 is at IO port A. And channel 3 is at IO port B. This is just how I've got them decoded. Now, you don't have to follow this if you're building your own computer. You can decode your IO ports wherever you want. You'll just have to change these equates. So this software should work for you no matter where you put the ports, as long as you change these lines right here. Now, next down here, I've got some more equates. These are divider variables. We're going to be taking the input frequency to the CTC, which is 1.8432 megahertz, and we need to divide that down to get the common baud rates. Now, I'm targeting 19,200 for my baud rate. Why? It's kind of arbitrary. It's just my standard go-to baud rate, okay? You can go faster, you can go slower. It's up to you. So to get 19,200 from 1.8432 megahertz, we need to divide it first by 6, which is what the CTC is going to do. And then we need to divide it by 16, which is what the SIO is going to do. So we just need to get the divide by 6 out of the CTC. And simply by changing our divisor here in the CTC, we can get different baud rates out of the SIO. It's that simple. You can change it on the fly in software. A lot of computers back in the day, early days, they had hardware counters to get their baud rates, and you were limited to only a few different baud rates, and you used to have to get in and switch jumpers around to change baud rates. When the CTC came out, it was programmable. You could change your baud rates on the fly in software, and you can do other neat things with the CTC, which we may dive into in the future, like having a periodic tick interrupt the processor, so we can time things. So that's down the road. That's another project way down the road. So we've got our addresses for the 4 channels of the CTC. We've got our dividers here. So we're going to dive right into the program. Origin is at 0. First thing we're going to do is disable interrupts. Nothing on my board is going to be generating interrupts, as far as I know. But it's always a good idea to disable interrupts if you don't need them, just so nothing happens, okay, and screws you up. XOR A, all that does is that's just going to load 0 into the accumulator, okay? It's just a really quick way to get the accumulator to 0. You can just explicitly load A with 0 if you want. It just takes a few more machine cycles. But I just go XOR A, the accumulator is all zeros. And then what we're going to do is we're going to load the diagnostic port with A. So all the lights on the diagnostic port should go out, okay? Then we're going to come down here to CTC init. And we're going to load the control word into A, okay? And this control word, if you go and you look in the CTC data sheet, so if you look at the CTC data sheet, every bit in the control word means something, okay? So the number we're putting in, 5D, basically is telling it that, well, this is a control word. We don't want to reset. Time constant follows. This doesn't matter because this is in timer mode, but we're going to be in counter mode. Edge selection doesn't really matter. I think we're going on the rising edge, but it doesn't really matter. Prescaler value doesn't matter because this is only for timer mode again. Counter mode, we're in counter mode. We're going to disable interrupts. So basically 5D is what you want to send out to your CTC, and that's what we've got here. So 5D sets all those bits just the way we want them. And so we're going to load the accumulator with 5D. So we're going to send it out to channel 0 of the CTC. Now, because we said time constant follows here at bit 2, the next thing we send out has to be our time constant, okay? So in this case, we're going to take our CTC divider, which we set to 6 up here, and we're going to load that in the A register, and then we're going to output the A register to the CTC channel 0 again. So we just told the channel 0 to start up, dividing the input clock by 6 and output the result. And that's what it's going to do. And then we come down here and we're going to do the same thing for channel 1. You don't have to set them to the same baud rate. You can set them to different baud rates. It's quite common to have different baud rates coming out, or I should say different bit rates coming out of different channels of the CTC. You might have like a fast accessory attached to one and a slow accessory attached to the other, and you might have to change those rates. You might have like, a fast serial terminal on one channel and a slow modem on the other. So yeah, changing the bit rates between the different channels is quite common, but I'm just, for testing purposes, I'm setting them both to do the same thing. So we're going to load A with 5D again. We're going to output it to channel 1 of the CTC. And then we're going to load A with the CTC divider 1, which happens to be the same as divider 0. And then we're going to output that to CTC channel 1. so we programmed channel 0 and channel 1 of the CTC. They both should be putting out a bit rate which is 1/6 of our 1.8532 megahertz input, which will be 307.2 kilohertz, if we did it right. So we'll have to check it. And then down here, what we're going to do is going to load A with 1 hex, and then we're going to output it to the diagnostic port, so the D0 light on the diagnostic port should come on, and then we're going to halt. And that's all this does. I mean, basically, the actual programming of the CTC takes place in these, 8 lines, basically. 8 lines of code. That's it. The CTC is initialized. All the rest of this is just, set up and, a little bit of fluff to show that the program's running right. I like to have some sort of visual indication that the program's running right, because if I don't get what I want out of the CTC, is it a problem with how I'm programming the CTC? Or is my program not running correctly? Is it crashing at some point, getting stuck in a loop, whatever? So by programming the lights on the diagnostic port and turning on the halt light, I can tell that the program has run to completion. And if I'm not getting what I want out of the CTC, well, I've done something wrong. So, okay. So let's compile this. Okay, it compiled. So let's download the hex file. It's very short. I'm going to program this into a 32K EEPROM, and it's it's a very short program. 99% of the EEPROM is going to be unused. Okay. Let's go over here to our EEPROM programmer. Going to load the file. Let's see here. There it is. That's the one I just downloaded. Okay, and let's see, it's set for 28C256 EEPROM, and we'll program it. Okay, let's pop the EEPROM out of the programmer, head over to the JAZ80, and see if it works. Okay, we're back. The computer's obviously working because our scanner program's running. So let's shut this down. Pull out the EEPROM with our scanner program in it. And put in the EEPROM we just burned with our CTC initialization code. Okay, let's power it up. Alright, hey, look at that. Our program ran. We get the bit rate out. We're on channel 0. Let's move it over to channel 1. See, yeah, we're getting it out there too. What's the frequency, Kenneth? 307.2 kilohertz. That's perfect. 307.2 kilohertz divided by 16 would give us 19,200 baud rate that we want with our SIO once it's installed. Because we'll set the SIO to have a divide by 16 prescaler. So that would be perfect. Okay, perfect. Exactly, it's working exactly right. The program ran. It set up the CTC registers. It lit the D0 light here, and then it halted, and the halt light came on. So everything worked just the way it was supposed to. Perfect. All right. It's pretty simple programming the CTC. It is not rocket science by any stretch of the imagination. As you saw, it just took a few lines of code to get the CTC up and running and putting out the bit rate we wanted. Okay? So, that's working. So in the next video, we can tackle something else. And I'm thinking the next video is going to be all about getting the SIO in and seeing if we can get some kind of like hello world message out of it. Might still do that, but I also want to revamp the reset circuitry. I'm really not liking it, so we might be able to have a twofer in the next video. Do both those things, so we'll see. So anyway, I hope you found this video interesting, educational, informative, enlightening, whatever. Killed some time, whatever. Give it a like, give it a thumbs up, and subscribe to see my future videos, because there's going to be a lot more coming. The JAZ80 is coming along. It's coming to life. So yeah, subscribe to see those future videos, and check out my main channel, Omega Geek 64. That's where all these chips came from. I salvaged them from e-waste. So that's what I do over there all day, every day, is work with e-waste. So check that out if you're at all interested. And I will see you in the next video. Thanks a lot for watching this one. Bye.